Hello, this is Jake Pickett with Andrew Sheedy and Sean Brennan, and this is the aerodynamic analysis of the Pat Pat rocket. Children's TV show known for introducing kids to different arts and cultures throughout the world. Little Einsteins go on adventures in what's called the Pat Pat rocket by flying around different parts of the world. Members of Team 44 have had a great interest in the show since they were children and wanted to use the opportunity in this project to explore the likeliness of the Pat Pat rocket being able to fly in a real world situation. The objective of this project is to identify if the Pat Pat rocket would be able to fly in real life. To do this, the team will analyze the relationship between the lift and drag forces acting on the Pat Pat rocket. The Pat Pat rocket will be able to fly if the upward lift forces are greater than the downward gravitational forces. As well as this, the relationship between the lift and drag coefficients will be able to tell us how aerodynamic the vehicle is. Lastly, dynamic and geometric similarity will be used to relate the findings to a real-life sized model of the rocket.
Instruments. Team 44 used the wind tunnel in the Potter 160 laboratory. In the top right, you can see the wind tunnel schematic. As the wind comes in through the intake, gets compressed and goes through a test section, and then finally goes out through the fan exit. The test section being used in this case was 30.5 centimeters wide, 30.5 centimeters tall, and 61 centimeters long. This gave us enough space to place our 3D printed model inside and properly mounted without hitting the walls or the top or bottom. The main instrument used in this experiment was the linear variable differential transform, or LVDT, and this was able to measure the displacements based on the lift and drag forces being experienced inside of the test section that were being impacted on our model. The test model was our Pat Pat rocket, and it can be seen in the CAD model in the top left, the overall dimensions and shape. The total length was about 5.62 inches, total width 4.99 inches, and the total height 2.06 inches. The overall geometry can be seen in the CAD drawing. As for mounting, the mounting devices being used were of 0, 10, and 20 degrees. The CAD drawings for these mounts can be seen on the right side of the slide. The mount was uh, used a hole that was able to thread onto the mounting screw, and also had a slot connection that was an interference fit with the bottom of the Pat Pat rocket to ensure a tight connection and mounting ability. 5 different angles of attack, as well as 5 different speeds, and tracked data for all of these different inputs. The testing speeds being used were 0 Hz, 10 Hz, 20 Hz, 30 Hz, and 40 Hz, which is about 0 meters per second, 5.506 meters per second, 13.952 meters per second, 22.398 meters per second, and 30.88 meters per second for the wind speeds going across the test section. As for the angles of attack, the team tested the Pat Pat rocket at -20, -10, 0, 10, and 20 degrees of angles of attack. For the experimental room conditions, the team used the thermometer inside of the room and measured 20 degrees Celsius, which is 293.15 kelvins. They also measured the pressure of the room using the barometer and found that to be about 740 millimeters of mercury, or about 98,763 pascals. The air density was calculated to be about 1.17 kilograms per meter cubed, and the air's dynamic viscosity was calculated to be about 1.8 times 10 to the negative fifth kilograms per meter per second. The assumptions in this experiment were that the flow is steady, incompressible, and along a streamline.
Took the LVDT readings and then processed the data on MATLAB to convert the voltage outputs to newtons and as well as coefficients of lift and drag. First, on the left, the graph displays the lift force for each of the rocket angles as well as Reynolds numbers. For each line, as Reynolds numbers increase with velocity increases, the force, either positive or negative, also increases and gets further away from zero. As expected, the rockets angled upwards at 10 and 20 degrees had a positive lift force as it was being pulled up off the LVDT, and the rockets with a negative angle were being pushed down into the LVDT, presenting a negative lift. On the right, drag force is displayed, also increasing with Reynolds number as we expect, and instead of positive or negative being the main factor indicating the amount of drag, it's the absolute value of the angle of attack. So at 20 and negative 20 degrees of attack, the drag force is highest at over 1.2 newtons, while at the more conservative angles, the drag force is less. We were able to create graphs of the lift and drag coefficients for all of our data. For both lift and drag, at the very lowest Reynolds number, the coefficient is inconsistent with the rest of the data, which indicates that we weren't able to get an accurate representation of the coefficients at lower wind speeds. So we're going to focus on the 3 higher wind speeds that we tested. For lift coefficient, similar to the force data, the negative angles of attack have negative lift coefficients as they cause the ship to go down, and the 0 and above angles of attack, since they lift the rocket ship up, have positive lift coefficients, which increase roughly linearly with the angle of attack. Looking at drag coefficient, again, the trend is similar to the force plot, where the absolute value of the angle of attack is determinant of drag coefficient. So the angles with 20 and negative 20 had the highest drag coefficient, and the shallower angles did not have as high of a drag coefficient. Data from the 3D printed model, we wanted to convert this data to be applicable to the actual size rocket. We don't have actual numbers for the real-world equivalent of the rocket. However, we made calculations based on enough room for the 4 main characters of the show to be able to fit in the rocket. So on the left of the chart are the 3D printed model dimensions and factors, while on the right, the full-scale equivalents scaled accordingly present much greater size, volume, as well as weight for the rocket. And importantly, the gravitational force is much heavier. However, the maximum lift is still well above that gravitational force, indicating possible flight. With that maximum lift force being greater than the gravitational force, we can see that with 20 degrees angle of attack, the flight is possible with pure acceleration. In addition, 10-degree angle of attack is also suitable. While 0 degrees was not able to generate enough lift to lift the rocket above the ground, if the tests were conducted at higher speeds, due to the trend of the lift force, flight would be possible, we project. However, as expected, the negative angles of attack prevent flight and push the rocket into the ground.
Future testing conditions could be to operate the test at more angles. So rather than just stopping at 20 degrees, we can go all the way until the stall angle. We could operate at more wind speeds or increment at smaller intervals. So rather than incrementing at 10 hertz, we can increment from 5 hertz. As well as this, we could do a larger scaled model, use a different material so rather than a 3D print, could use a more realistic material that applies more to the weight of the realistic pat rocket. We could also use a different mounting device or methods and use more turbulent wind. Feel free to email us any questions you may have.